All right. Well, hello and good day to you all. Sorry, I didn't update. It's Tuesday. But week two, and I hope you guys are doing well. Just got back from the R conference, and I had a great time there. A lot of kind of new developments, especially things involving AI, talking with chatbots, LLMs, and kind of harnessing that kind of power. Um, there's one of the things that was brought up is, is R still a worthwhile language, especially when so many things in industry are moving towards Python and whatnot. And well, I mean, this, of course, I'm going to get a biased response from the people at the R conference, okay? But the I, you know, they argue that R is still definitely worthwhile to learn because R is really designed around data science and data analysis. It's really designed in such a way, like natively, it handles, vectors and matrices and data frames just kind of as part of its core identity. Whereas Python can handle vectors and data frames, but that's after you load libraries. And Python is very much a general purpose language, and so Python does a lot of things very well. But R is always going to kind of have, I would say, data analysis and data science at its forefront. Especially when it comes to data visualization, I think ggplot and R's graphic tools can't be beat, really. There's also kind of, especially with chatbots, LLMs, and AI. One of the things that LLMs and AI does really, really well is translation. Okay, not just translation from like English to Spanish, it does that really well, but also translating from one language to another in terms of coding. And so you can ask, you can provide the code in R and say, can you translate this into Python? And vice versa, can you translate this into Python and back into R? And you'll get very good results, and it will be better than just saying like, hey, here's my problem, write a solution for me. And the AIs can do that, and it can produce solutions on its own. But in general, you will get what you want a little bit better if you give it, if you kind of constrain it more, right? If you say, hey, these are specifically the functions and the tools I want you to use, and things like that. Or again, if you have something already written out that works well in R, you can just say, hey, translate this into Python. Or if you have something in Python, say, how do I do something, do the equivalent thing in R using these packages or whatnot. And so there's a lot of kind of things there. There were some cool packages that they introduced. One of them was called Elmer. This is part of the R tidyverse. LLM is kind of the part here, and it's made so you can kind of interact between, you can chat or interact with these AI bots and whatnot. To make use of it, you'll need to get like a developer API key. So you'll have to create like a developer account with, say, like OpenAI, and then you'll need to kind of give them a credit card, say like, and then you have to put like $5 on your account. But that will take you very far. Okay, they have different models. Different models have different pricing. I think Google's Gemini also comes with a very generous free tier, and so you can kind of create like a developer account and get an API. So anyway, this is completely unrelated to our course, but it is kind of cool. And so, perhaps, I don't want to make any promises that I can't keep. So I'm going to say perhaps kind of like the very last lecture when, I guess, right before your final exam, where I'm not going to be giving you a whole lot of like heavy content or anything like that. We can just kind of play around with some of these things and take a look. But But yeah, I guess when we think about AI, I am convinced. Not everybody's convinced, but I'm convinced that AI is going to be like, it's here and it's going to kind of stay. It's not. I don't think it's like a tech fad. I don't think it's like, I don't know, NFTs or something where it's just like exciting and then it like disappears or something. I think it's going to be around, and we do need to learn how to use it. We do kind of need to make use of it. But again, as I've been saying, you don't want to offload like your critical thinking, right? Like this, your own ability to think and reason and make decisions and critically think about things, like that is going to be important to you. So you want to kind of keep that, and we want to minimize we don't want to offload that critical aspect of our being and our consciousness to the AI. Okay. And so it is I do think it's going to be an important tool that we have to learn how to use. Use it for what it does well, like translation, maybe like refining some of your stuff, but like completely generating things, not taking away your thinking, not ideal. But okay, anyway, that's enough about that. Let's talk about today's stuff, and we will take a look at gradient descent. Gradient descent is one of the most important kind of optimization algorithms that are in our disposal for kind of finding optimal solutions. Okay. And so if we kind of just go back a step, we've been talking about finding the solution to a problem, okay, like minimizing the sum of squared residuals. And the way we've been doing that is we've been using calculus, okay? So when we talked about like for least squares regression, whether it's simple linear regression, multiple linear regression, we said this is our how we measure our loss. We take the difference between our target value and what our function is predicting. We say that this difference is the residual. We square them, we add them up. I guess this is not the sum of squares, but the mean squares residuals. And we're going to say we want to minimize this thing. We want to find the values of the slope and intercept or whatever that's going to minimize this. And the way we did this is we used calculus. We say, hey, what is the derivative of this thing? Let's set the derivative equal to 0. Let's solve for where that derivative is equal to 0, because that's where we expect to find the minimums. And that's how it worked. We did that. You can do it with partial derivatives. We did it in vector form, and we got x transpose x inverse x transpose t. That's what we did. Okay, and it was straightforward and simple enough when this function is like a linear thing. Okay, and we can kind of multiply it out and expand it. But sometimes this function gets really complicated, okay? And so, I think in our next lecture, I'll introduce like neural networks. And this part, even in like the simplest case of neural networks, this part gets kind of complicated, and it becomes a lot harder to, or maybe even impossible to try to use calculus and whatnot. Or maybe you can find the derivative, but then solving for where it's equal to 0 gets really hard. And so we'll use some of these computational methods, okay? And so, the goal is still the same. We still want to figure out what is the slope, what's the intercept, or what are these weights, what are these parameters that are going to minimize the loss function. We want to, this is our objective function. We want to find this set of values that are going to minimize this. And when we do that, we're trying to find the set of values that will minimize it for our particular set of data. So we set our data as fixed, okay? And the loss function is a function of the parameters that we're able to, that we're trying to estimate, the ones that we're trying to adjust. So in the case of simple linear regression, We just have two parameters that we're trying to adjust. We're trying to figure out the slope. We're trying to figure out the intercept, okay? But certainly, you know, other neural network, things like neural networks, you're going to have, you know, dozens, hundreds, perhaps millions or billions of parameters, and you want to be able to find the right set of values, okay? And so we will introduce gradient descent. If you took 102A, so kind of the previous class in our sequence or whatever, at least with me, I covered coordinate descent, where you optimize one variable at a time. And, you know, there's a similarity to it, but here we're doing gradient descent, which depends on us finding the gradient or the derivative, right? So when you have a univariate function, if you have a function of one variable, a single variable, the derivative represents the slope of the tangent line to the graph, okay? And then, but in our case, we have a function of multiple variables, okay? And so the kind of multivariate analog to the derivative is the gradient, okay? And the gradient will point in the direction of greatest increase, and the magnitude of the gradient is that the rate of that increase. And the idea behind gradient descent is that if we're at some location on our kind of response surface, okay, we use the gradient to point uphill, and then we take a step in the opposite direction, which will be downhill, okay? So we move in the direction opposite of the gradient. This points us downhill, and if we repeat this process over and over and over again, eventually, if we keep taking steps downhill, that should reach, eventually we should reach the bottom, okay? We should reach the bottom of our valley, okay? And so the algorithm for gradient descent is very, very, very simple. Basically, the algorithm is take wherever you are, find out which way is uphill, and then take a step backwards. Okay, and that's it, right? So just take steps downhill. That's it. Keep taking steps downhill. And so this is it, okay? We have some function. This is the function that we are trying to optimize. We want to find the minimum of this function f. So we could think of f as maybe like the sum of squares residuals or the mean squared error or whatever it is. This is the function that we want to minimize, okay? Our current location is at location w, so this will be a current estimate of our slope and intercept, or a current estimate of whatever parameter values you have. So this could exist. So in the simple case, we have, it's a two-dimensional vector. We have a slope and an intercept. Currently, my slope is 2 and my intercept is 1, whatever, okay? But you could have a high-dimensional vector w, you know, exists in 17 dimensions that we can't really picture, but that could be. And we're just going to say, okay, currently, my estimate of w is an intercept, what did I say? We'll say an intercept of 1 and a slope of 2. Okay, that's going to be my current value. And then I find the gradient of this, and it says the gradient points in this direction. And then all I do is I just take my thing and I just subtract off some constant. This is a gamma here is a positive constant, less, not necessarily less than 1, but just some positive constant. This is a scaling factor, and I will multiply it by my gradient. Sometimes the scaling factor is lambda, but it's the same idea here. Okay, and we just do that. And then all we do is we just take our current value, subtract off some scale times the gradient, and that gives me the value at my next iteration, my value at w at time n plus 1. And that's it. And I just repeat this, and I say, okay, now that I'm at this thing, let's find the gradient. So, you know, it's kind of like, I don't know, it'd be like the worst instructions, but like you go on a hike and you say, oh, let's meet at the bottom. I'll meet you at the bottom of the hill. Okay, and you go, well, how do I get to the bottom of the hill? And then the instructions are, look around and find out which way is downhill and take a step downhill. Okay, and just keep doing that. If you keep taking a step downhill, you'll get to the bottom of the hill. And that's kind of true, right? Especially if it's a simple, if it's not a crazy jagged canyon, okay? But if it's like a simple straight, shape, just keep taking steps downhill and I'll meet you at the bottom, right? It's kind of like you can imagine releasing a bowling ball and letting it just roll downhill, okay? And so let's do an example of this, okay? So here's just some arbitrary function of two variables, x1 and x2, all right? And so the function is x1 squared minus 2x1 minus 0.5x1 x2 plus 2.5 x2 squared, okay? And we will kind of do this mathematically. And so I'm going to say, all right, let's take the gradient of this thing. So the gradient of this is going to be the vector of partial derivatives. So we're going to say, what's the partial derivative of f with respect to x1? What's the partial derivative of f with respect to x2? So the partial derivative of this with respect to x1 is going to be 2x1 minus 2 minus 0.5x2, and that zeroes out, okay? And then what's the partial derivative of this with respect to x2? So this zeroes out, and then I get minus 0.5x1 plus 5x2. Okay, so I have two components in this, in our gradient, the partial derivative with respect to x1 and the partial derivative with respect to x2. Okay, and so if I plot the function, this is kind of what it looks like, and my minimum is located at the bottom of our hill here, and so it's just kind of, this is a contour plot, and it's basically, if you plot this, it looks like a big bowl, okay? And the minimum is located right here. And so we will do, okay, so this is my 3D plot. Yeah, again, it looks like a big bowl. And so I'm going to start off at this arbitrary location of -5, 4, okay? So x1, -5, 4, this puts me in the top left corner, right? So, the analytic method is we would say, here's our partial derivatives. We set everything equal to 0. We have a system of equations. We solve for x1 and x2 or something like that, okay? But here, we're not going to bother with that. We're going to do, we're going to just do this computational approach where I iteratively just kind of refine my value. So I'm going to start off at this arbitrary location, -5, 4, okay? And so I plug in -5, 4, and that is going to be my gradient. The first component, when I plug in -5, 4, I'm going to get -14. And if I plug in -5, 4 into my second component, I get 22.5. Okay, so the gradient at this location is a vector, -14, 22.5. And so that points in the direction of greatest increase. Okay, and the way I'm going to update is I'm going to take my current value. So this is x1 and x2 at time, subscript 0 means at time 0. So I'm going to have -5, 4, and then I'm going to use a scaling factor of 0.1. So I'm going to do minus gamma times the gradient. So my gradient is -14, 22.5. I'm going to multiply by 0.1, okay, -0.1. So this is going to become 1.4 and -2.25. And so if I do -5 plus 1.4, that gives me -3.6. And 4 minus 2.25 gives me 1.75. So that's going to be my next location. And so if I plot this, so I start off at -5, 4, and my next iteration is, what was it, -3.6, 1.75, and that's right here. And so taking one step down looks like this, okay? Here I just have this coded up in R. I'm just going to take my function, x1 squared minus 2x1 minus 5x1 x2 plus 2.5 x2 squared. So my function is going to be this. And then the gradient is basically I'm going to just return a vector of basic partial derivatives. So the partial derivative with respect to x1 is this, and the partial derivative with respect to x2 is this, -0.5x1 plus 5x2. So that's what we have there. And I'm just returning the vector of partial derivatives. So, and then if I plug in, if I say I'm going to start at -5 comma 4, I can say what is the gradient, and I get -14, 22.5, which is exactly what we got right here. And then I can say, all right, take my starting value of -5 comma 4, subtract off gamma of 0.1 times the gradient of that thing, and we get -3.61.75. Okay, so this is basically all I'm doing is I'm just turning this page of math into code, and it's a direct one-to-one translation. Okay, and so I do this, and then I can plot that, and so this is -5 comma 4, and this is -3.61 comma 1.75. And so that is one iteration of gradient descent. And now that I'm here, I'm going to do the same thing. I'm going to say, all right, if I'm at -3.6 comma 1.75, what is the gradient at this location? The gradient at this location is going to be this. And I say, okay, now multiply this by 0.1 and subtract that. So I'm going to take my -3.6, and I'm basically going to subtract -1.0075, and so that gives me -2.5925, and then I start off at 1.75, and I subtract off 1, I move the decimal over, 1.055, and I get 0.6950, and so after 2 iterations, this is going to be my location, -2.59 comma 0.695, and that's right here. So that takes me right there. And then I just repeat over and over and over again, okay? So here I'm going to just run a loop. I'm going to say, okay, let's start off at -5 comma 4, and this is the gradient descent algorithm. I'm going to just say, I'm going to just run 20 iterations of this for I in 1 through 20. Just do, this is the gradient descent algorithm. Take your current value of the x vector, subtract off gamma times the gradient at your x vector location, okay? And update your x vector there. And then with each iteration, just store whatever that is into row I. So it's going to start off, store -5.4, I'm sorry, -5 comma 4 in the first row. It updates it, stores it at the second row. Keep doing that, and so we do that 20 times, and then I'm going to plot, create a plot of all of these arrows. The function for arrows is basically your starting x and y and your ending x and y. So I'm going to start off here, and we'll end at the next row, right? So we start off at row I, first column, row I, second column for x and y of our first row, and then we'll end at row I plus 1, first column, and row I plus 1, second column. So this basically, I do this, I'm going to get 19 arrows, and we do this, and this is the plot. And so you can see we started off at -5 comma 4, and we end up here, and then we go here, and so those 2 arrows are exactly the same as right here. And then we just kind of keep going, and you can see we're just kind of going downhill, and you know, as we go down the hill, our steps get smaller and smaller and smaller, and eventually we will end up at the optimal location at the bottom. All right, let me give you your first view quiz answer. First answer today is the letter B. B as in bear, B. Okay, does that feel all right? Okay. If I choose smaller gamma, basically I'm just taking small steps, all right? So 20, so here's gamma 0.1. If I choose gamma 0.03, same plot basically, but I'm taking smaller steps. So same algorithm, so basically it's gonna take more iterations to kind of reach the bottom here. And so we're just taking same, following that. If you have a bigger gamma, then you're taking bigger steps, and we end up here. If you take too big of a gamma, okay, now we start like we've overshot. Okay, so this is what I call the shower problem, where you know, if you have sometimes you your shower, it's like, oh, it's too hot, so I want to adjust it, and you tilt it, and it gets too cold, and you're like, oh no, it's too far, and so you have to go back and forth, right? And so this is this. So sometimes if you have too big of a gamma, you've gone too far, and you have to kind of go back and forth, and you kind of have this back and forth business, okay? And then sometimes like and this is like, I don't know if you've seen like a car fishtail with because it's got like too much weight in the back. Like sometimes if you take too big of a thing, you end up like you know, you're swinging back in the opposite direction. The swing back is like even bigger than it was before, and then you swing back in the opposite direction, it's even bigger, and so like now you're like really losing control because it's you know, I don't know, things get overcorrected and like by, you know, too much, and so it swings in the opposite direction. So sometimes you know, having, you know, too big of a gamma, you can really overshoot and not just end up being inefficient of kind of going back and forth, but now you're like, your swings are with each swing you're overcorrecting, and it's like this feedback loop of overcorrection, and it just kind of blows up. So that could happen too, right? So gradient descent, as great as it is, there is no guarantee that it will converge, and there's no guarantee that it will find the correct value. So it's a very simple algorithm, and it's a very useful, and we use it all the time. But yeah, there's no guarantee that it's gonna work. Okay, and a lot depends on what gamma you choose. Okay, so you know, all I'm doing is I'm just choosing different values of gamma. Here it was 0.1, 0.03, 0.15, and just choosing the wrong gamma can be the difference between it converging and not converging, okay? And unfortunately, there's no magic answer for what the right gamma is, okay? A lot of it is trial and error. You know, you just try one out and you hope it works. And so, you know, the recommendation is start small, and if it looks like it's working, then, you know, start small and do a trial run, okay? And if it looks like it's working on the trial run, then you can try pushing your luck and increasing it a little bit, and then do a trial run again, see if it still works. And if it looks like it's improving, then you keep kind of pushing until you're like happy, and then you can kind of run it fully, okay? But then you might find, oh no, I picked too big of a gamma and it's no longer working, all right? And then, you know, step back. So it's kind of start small, increasing, and then do trial runs to make sure it converges, and then you do that. There's other people have taken a lot of taken gradient descent and have tried to do a variety of things to improve it. And you have these ideas of like simulated annealing and ADAM, which is these these extended versions of gradient descent where you adjust the gamma as time goes on. So, you know, you start off with kind of big changes, and then as you're getting fine tweaking things, you can adjust them down, and things like that. So there's things, but we'll just kind of stick with simple gradient descent. They have ones with like momentum and stuff. Okay. So here I'm going to demonstrate how gradient descent can be used on a problem like ordinary least squares regression, okay? So we already understand ordinary least squares regression. There would be no need for us to use gradient descent for this, because this is already a solved problem. Like, we know the solution that's going to give us the best fitting slope and intercept for OLS, okay? But we'll start here, because we know what the answer is, and so we can use gradient descent, and we can see, oh, is it going to give us the answer that we know is correct, all right? And so that will be kind of like a proof of concept that, like, oh yeah, so this method also works, right? And therefore, when we start doing problems that we don't know like we don't have a solution for like OLS, we can feel like, okay, well, gradient descent worked in all these other cases. We're hoping it's going to work in these cases, and a lot of times it does. So, so this is what we are doing. So when we do ordinary least squares regression, we know, so this is the loss function that we're trying to optimize, which is just the mean squared error, and this can also be written in matrix form, which is t minus xw transpose, and we spent a whole lecture talking about that. And we said, okay, you know, we could find the partial derivatives, okay, and we can say, here's the partial derivative with respect to W0, here's the partial derivative with respect to W1, okay, and if we want to do it in matrix notation, here is going to be our the gradient, okay, and this will automatically kind of, when we do in vector notation, this vector right here will basically consist of our partial derivatives with respect to W0 and W1, okay? So this is how we're going to find the gradient, okay? So we could do the gradient either with partial derivatives or in matrix notation. I think I use matrix notation just because it kind of keeps things simple, okay? And so how we would go about doing this in the gradient descent algorithm is basically we take our current existing vector and we subtract off gamma times the gradient at our current location. If we're doing it in the notation of partial derivatives, we have the vector of our components, W0 and W1, and we would subtract off gamma times the vector of our partial derivatives, but this is kind of the same idea here, okay, in matrix notation. All right, so I'm going to just start off with this very, very, very simple data set. There's only 3 data points. X is 1, X is 3, X is 5. And the target values, we have 1, 4.8, 3, 11.3, and 5, 17.2. And we can fit a linear model. And when you fit the linear model to this, we get a slope of 3.1 and an intercept of 1.8, okay? And if I plot this, this is what the picture looks like. So our values were 1, 4.8, and you can see if I plugged in x equals to 1, I would get 4.9 or something. No, right? 3, yeah, 4.9. So our model predicts 4.9. The true value is 4.8. And if I plugged in 3, I get this value, which is a tiny bit different. If I plug in 5, I get this value, which is just a, so this is the best fitting line, okay? The best fitting line has a slope of 3.1 and an intercept of 1.8, okay? What we're going to do is we're going to run gradient descent, and we're going to try to try to find the solution of 1.8, 3.1 for my intercept and my slope, okay? So here I'm going to just create a function that's going to calculate the gradient in vector form. So I'm using vector notation. So I just have x transpose t, okay? So that's x transpose t plus x transpose xw, x transpose times x times w, okay? And here I just I got rid of this factor of 2 over n, okay? This, I mean, I could include it, but it's just a constant. And remember, when we do gradient descent, we have some other constant gamma times this gradient here. And so basically, whatever gamma I choose, it will basically include like a factor of 2 over n or something if I'm concerned about that. So I'm just really worried about like, how is this affected by changes in our w vector? Our w vector being our slope and our intercept and slope. Okay, the x is our data, the t is part of our data, so these are all kind of fixed according to our data, and so these would exist in the global environment. And what we're really changing is just my w vector, and we just want to see how the gradient of the loss function changes as I change my gradient vector here, this w. Okay, so I'm going to just start off at a completely arbitrary location All right, I'm going to just say, you know what, let me start off with an intercept of -1 and a slope of 1.5. Okay, so the solution says the intercept should be 1.8 and the slope should be 3.1. But here I'm starting off with an intercept of -1 and a slope of 1.5. This is my initial W vector. I'm going to choose a tiny gamma of 0.02, and I'm going to run 1,000 iterations. Okay, so this is a lot, but the computer can do this very quickly. And really, you know, again, it's just one very simple line for the gradient descent algorithm. Just take your current value of the W vector, subtract off gamma times the gradient at your current gamma vector. And we let this run 1,000 times. And this is where we end up. We end up at 1.79995 and 3.1. So this is close to the solution of 1.8 and 3.1. Okay. So this seems like, okay, that seems to be getting us close to the answer. And probably if I let it run longer, we'd get even closer. And what I want to show you is just at a few kind of iterations of what our what gradient descent is doing here. Okay, so I'm going to plot these contours, and so this is just code to kind of get these plots going here. Okay, so this is a contour of the RSS. Okay, residual sum of squares for different values of the intercept and different values of the slope. Okay, so the minimum occurs right here where the intercept is 1.8 and the slope is at 3.1. So that occurs right here. And these contours are showing that, like, if you picked an intercept that was too high, okay, your RSS, or is it mean squared error, whatever it is? I'm calculating my loss. This is just the sum of squared residuals. You know, is going to be higher. And if you pick an intercept that's too low, your RSS is going to, you know, it's going to go from 0.025 to 0.5 to 1 to 2 to 3 to 4 to 5, you know, and it can keep going higher and higher and higher. And so, you know, you could have an RSS of 200. All right, so that's what all of these different kind of contour lines are. This red line shows the path of that our gradient descent algorithms took. Okay, so remember when the very initial value that I started off with was an intercept of -1 and a slope of 1.5. Okay, so an intercept of -1 and a slope of 1.5 is right here, and that corresponds to an RSS of close to 200. Okay, and it said the gradient descent algorithm basically was following the steps downhill, okay, and it kind of went downhill, and then it follows this. All right, so you can kind of think of this bowl, right, and the sides of the bowl are very steep. It's this very kind of like oval shaped bowl, right, and so when you drop the marble, it first goes down the sides of the bowl that are very steep, and then once it kind of reaches the bottom, then it falls down here. Okay, so this is the plot where here's my data. My data were the points 1, 3, 5, 1, 4.8, 3, 11 point something, and 5, you know, something else, right? So this is the data. And we can see if I start off with an intercept of -1 and a slope of 1.5, this is what the fitted line looks like. And we can see this is going to do a terrible job of fitting the data, okay? And basically I have these two knobs. One knob can change the slope, and one knob can change the intercept, okay? So you can kind of picture this as, I can get myself in here, okay? But basically, right now, this is the line that I'm fitting. Right? And And so, eventually I want to get something that fits like this, okay? So what I have to do now is I have to say, okay, well, should I slide the line up? Should I increase the slope of the line, okay? And so according to gradient descent, the gradient says the direction you need to go downhill is in this direction, okay? And so after one iteration, okay, after one iteration of gradient descent, we have increased our slope from 1.5 to 2.312. And I've changed my intercept from -1 to -0.772, right? And so this is the resulting line. So this line has a steeper slope of 2.3 and an intercept that's less negative at -0.7, whatever, right? And so we can see, comparing these two lines, neither of them does great, but this one does a better job, okay? So we have reduced our, sum of squares residuals, okay? At the next iteration, or after a few more iterations, so after 5 iterations, it says, it has brought us to here, where our slope is 3.33, okay, and an intercept of -0.459, okay? So now we've actually, remember the solution has a slope of 3.1 and an intercept of, what was it, 1.5, 1.8 or something, okay? 1.5 and a slope of 3.1, I think. And so we can see this line is actually just a touch too steep versus like the actual solution should be something like this. So we can see this, after 5 iterations, our slope is just a touch too steep, but our intercept is not high enough, okay? And so we're kind of like right here along our path. And eventually we're going to reach here where, our slope is maybe still too steep and our intercept is too not high enough. And then we start kind of adjusting things where we're going to, once we get up to here, we're going to start to kind of bring the slope down. Okay, we're going to decrease the slope, but at the same time at decreasing the slope, we're going to increase our intercept. Okay, so that's what moving to the right on the intercept axis means. You're going to increase the intercept, and then moving down on the y-axis means you're decreasing the slope. So basically, we're going to see the line kind of come up to here, and then we're going to kind of decrease our slope, but at the same time increase our intercept, right? And to try to kind of ideally find the perfect fit where the slope is 3.1 and the intercept is 1.5, whatever it was. Okay, and so that's what we see here. So kind of starting back here, we start by kind of increasing our slope a lot, and then as the lines go on, we're going to kind of see the line kind of get less steep, and the intercept goes up. So here I've just kind of iteration 1, 2, 5, 15, 100. This is after 300 iterations, and we get something kind of that's kind of the path of it fitting here. With the structure, with the way this contour lines are, it actually takes a lot of iterations to go from here to here to here. Okay, you can see it went from iteration 15 to 100 to 300. So it's just really just adjusting it just a tiny bit at a time. Because yes, question.
Are there any guidelines for convergence, like how close the iterations have to be together?
Yeah, convergence is always a tough question. Yeah, the guideline is whatever you can afford computationally, just let it run. And when it looks like things aren't changing much, then you say, all right, I think we've converged. It's not a great answer, but unfortunately, I don't think we have great answers here. And it's going to depend a lot on your problem, and also how much. So sometimes we run up against computational stability issues. So the numbers on your computer are floating point numbers, right? So if the two numbers are really close together, you actually can't detect that difference on the computer. So and depending on your data, if your response variable is a small value, like detecting changes is tough, and if you have big values, it's different. You might have to take the log of these things. So all to say, no, I don't have a good answer for figuring out convergence. Okay, it's a lot of times, you create a plot and you're like, okay, it looks like it's flatlined here. Okay, and that's where our hope is. Or you're looking at the log of the loss function, and at some point it looks like it reaches a straight line where it's just your loss is increasing, I guess just geometrically, just like your losses are shrinking by a factor of like 0.5 at every single step. And so when things when it looks like you've hit this asymptote, or just kind of like a straight line in the log function, that's when you're like, okay, I think we've converged. But yeah, I don't know. There's no guarantee that you're going to converge either. So, okay. So these are just illustrations of other things. Or if you pick a gamma that's just a little bit too big, then you run into, this is the shower problem, where you've overcompensated and you got to swing back and forth. Here it's still going to converge. It's going to get us to the right answer. Okay, so this is still kind of honing in on the right zone, so that looks okay. But if you pick a gamma that's much too large, so here I picked one where it's not that far off, but again, each time I'm swinging, and every time I swing, my swings get bigger, right? So like I'm overcompensating, and then I'm overcompensating, and then I'm overcompensating, so things just kind of spiral out of control. And so at least in this direction, we get it wrong. In the other direction, we actually kind of hit up against a wall here, but now we're like wildly all over the place. So that can happen too. Okay. There is a tool that we can use, and this is numeric gradient checking, all right, where we want to calculate the gradient kind of numerically, okay? So, to get the gradient back here, we used vector calculus to get this form here, and that's great, okay? But sometimes that can be tough, okay? So sometimes it can be difficult to find the gradient via calculus. Sometimes you go through the process, right, and you have kind of a tough problem, and you think you found the right answer, but you're not 100% sure in your right answer, okay? So one of the tools that are at our disposal is numeric gradient calculation, okay? This is an inefficient tool, so you don't want to use this as your primary method of calculating the gradient. But what it does is it's a good check for you to say, like, here I found the gradient analytically, or at least I think I did. Is my answer correct and reasonable? Okay, the numeric gradient method will give you an estimate of the gradient, and if they align, you're like, okay, I feel confident about how I calculated. Okay, so basically, try to find the gradient analytically via calculus, but then after you do that, use the numeric gradient check to just kind of make sure that your answers make sense, right? So the numeric gradient is based on the idea of, like, if you take the derivative, it's the difference as h goes to 0, and so you're just going to shrink, add just a tiny small epsilon or to an h here, okay? And here, when you think about the gradient, you can think of it as the vector of partial derivatives, and so you're going to find the partial derivative with respect to x1. So if you have a function of two variables like x1 and x2, you're going to add h to just x1, okay? And you leave x2 unchanged. And then for the partial derivative with respect to x2, you leave x1 unchanged, and you add h just to x2, okay? So you make sure you do these two things separately, and you add a small h to just one variable at a time. Like, I'll talk about your exam, I guess on Thursday, because I know it's already, we're going to take a midterm on week 3, and so that means that's next week. But anyway, you can expect to see a numeric gradient problem on the exam, and a common mistake that students make is that they add the h to both the x1 and the x2 in one step, okay? And you want to keep those separate. Add h to x1 all by itself, do that over here. Add h to x2 all by itself over here, okay? So if we do it for something like this, okay, we're going to do numeric gradient on our example here. And so first we're going to calculate what the value of the function is at our starting location of -5, 4. So I just plug in -5, 4. The value at my starting location is 85, okay? And now what I'm going to do is there's two components. So these are two completely separate things. One is I'm going to add, say, 0.01 to the first component of -5, okay? So -5 becomes -4.99, okay? And I know the function, when I plug in -5, 4 is 85. So if I plug in -4.99 instead of -5, the value of my function changes to 84.86, okay? So how much did that change? Basically, it went from 85 down to 84.8601, so it dropped by -0.1399, and I divide by how big was my h in the first place. My h was it was 0.01, so my numeric gradient here is -13.99. Okay, this is basically how much the function changed relative to h, which is this, okay? I do the same thing over on this side, except now I add my h of 0.01 to the 4, okay? So I'm going to plug in -5, 4.01. Okay, when I plug in -5, 4.01, the value that I get is 85.22525, okay? How does that compare to what it originally was? It originally was 85, so my function increased by 0.22525. And so when I divide by 0.01, I get 22.525. So my numeric gradient estimate of how much my function changes, my numeric estimate is -13.99, 22.525, okay? When we did the analytic result, okay, so that was way back here on this slide, what was it? Right here, okay? On this slide, the analytic result was -14, 22.5, okay? So on this slide, we estimate it to be -13.99 and 22.525, and we say, hey, that's pretty close to our analytic results, so we feel confident in our analytic results, and we proceed using our analytic results as we move forward, okay? So that's going to be how we do gradient descent. Okay. All right, let's talk about regularization. So this is kind of like a different topic here. This is a way for us to, I guess, tweak some of our estimates in linear regression or any other kind of model where we're estimating parameters, and we want to, in our bias variance trade-off, okay, if we're okay with increasing bias to decrease variance, regularization is one of the steps that we can employ. Okay. Oh, before I forget, I gave you just one answer so far. I'll give you your second view quiz answer, which is the letter B. Again, B is your second view quiz answer, B. Okay, so we have already talked about how to address overfitting by using, say, cross-validation. That's one of the ways we can avoid overfitting by, holding out kind of a validation set. We train our model on the training set and we compare it to the validation set to evaluate it. Okay, regularization is another way for us to avoid overfitting. Okay, and again, these are what it will do is it increases bias, tries to decrease variance, and it changes the loss function to by penalizing kind of more complex models. Okay, so again, we're going to start off in linear regression. Our loss function is the mean squared error, right? So we just take the difference between TXW, we square that, sum that up, okay? And we say, hey, you know what? The best model, according to this definition, is the model that's going to minimize the mean squared error, right? But we know if we say, hey, this is the only guiding principle, then we end up selecting models that are far too complicated, okay? If you say the only thing, basically R squared is a measure of like how much of the model is how much of the variance is explained by the model, and if you're saying I want to maximize R squared, you're going to say let's include all of the predictors, right? Because if you include all of the predictors, you can always kind of edge out R squared a little bit more, okay? If you say let's fit a 20-dimensional polynomial, you can always kind of increase the fit if this is the only thing measuring it, right? And we say, all right, well, that's obviously not a great great way to go about it, okay? And so what we're going to do is we're going to modify this loss function, and the loss function itself is going to now account for how complicated the model is. Right? And we're going to say, hey, if your model is too complicated, you're going to get a penalty. You're going to get a penalty for your loss function. Okay. And you saw an example of modifying the loss function in your homework when you did weighted least squares. So you had this vector of weights, and that's going to say, hey, these residuals are more important than other residuals, and so it ends up kind of shifting how the thing ends up fitting. We're going to do something different, similar but different, in that we're going to modify the loss function, but the way we're going to modify the loss function is one that's going to penalize overly complex models. Okay, so all we're going to do is we're going to say the total cost of something is going to be the loss function, okay, which is here, our sum of squared errors, our mean squared error, plus gamma times complexity, some measure of complexity here. We're going to include that in here, right? So it's kind of like it's like a tax, okay, a tax for complexity. So when you start thinking about what should you purchase, okay, what should you pick? Now you have these different kind of things to consider. Okay, so here this is we're going to call this our regularized loss, L prime. This prime here, the little here is not doesn't mean derivative. Okay, so like in some notation, some textbooks, like the prime means the derivative. We're not saying that. The L prime here is just, it is the loss, a function related to the loss, but not directly that. Okay, so this is the loss function, the original OLS loss plus penalty for complexity times lambda, okay? And lambda is going to be kind of a factor that we can use to say, like, how big of a penalty should we apply? We can make lambda really big and say complexity gets heavily penalized, or we can make lambda really small, or lambda 0. Lambda 0 basically means no penalty for complexity, okay? So we can choose exactly how much penalty should be applied, okay? My analogy to real life, all right, this is how do you factor in different kind of criteria for things that are important to you, right? So if you're like trying to pick an apartment, where do you want it, like which apartment should you rent? Okay, there's lots of different factors, but let's just say two important factors are going to be like, how much is the rent at the apartment? Okay, obviously you want to have a low rent. You don't want to pay too much for an apartment. Okay, and then the other part that might be important is like, how far away is the apartment from where I need to work or go to school? Okay, so you might say, well, it's really important for me to be close to work. Okay, or you know what, I don't mind commuting a little bit. Okay, and so these are going to be things to consider. And so, you know, we could say, hey, one apartment that you're considering is $2,400 a month, and the commute is 10 minutes each way to work. Okay, the other apartment is cheaper, $2,000 a month, but the commute is 40 minutes each way. Okay, and so which apartment should you pick? Okay, so if money is the only factor that matters, then it's easy, pick the cheaper apartment. Okay, but for most people, you know, now you have to trade off, and you have to ask yourself, how much is my time worth, right? What is the conversion factor between this comes with a penalty of like, now I have to commute like basically an extra hour a day, right? And how much is that worth to me, right? So you know, here your total commuting time is 20 minutes. Over here your total commuting time is 80 minutes. And so you're commuting an extra hour a day, and you have to ask, how much is that worth to me, right? So an extra hour every day, you know, if I'm commuting to work 20 days a month, okay, how much is that worth, right? So if is saving an extra 20 hours a month worth $400 a month to me, then you would say, yeah, it's worth paying the extra money. And if you're saying, yeah, no, it's not, then you go with a cheaper apartment, right? If you have that luxury of kind of these things, right? So if you value your time greatly, right? So if you have like an active social life outside of work, or you really hate commuting, you'd weigh the penalty of the longer commute much heavier, and you'd end up picking the apartment closer to work, right? Even though it costs more, right? On the other hand, if you don't mind the commute, okay, don't have a whole lot to do outside of that, and you're like, you know, I don't mind the commute, then you'd probably pick the apartment with a lower rent. So the true total cost of the apartment, or the true cost of the apartment for us to kind of compare. So basically we're trying to take these different criteria and boil it down to a single number that we can compare, right? So to get a single number, we have the true cost of the apartment, we have the rent itself plus our preference factor, whatever that is, times the commute penalty, right? An extra hour a day. And how much is that? Is that worth an extra hour a day? Is that worth saving $400 a month, right? And depending on that kind of factor, what is it? What is it to you? Okay. We're still kind of optimizing a loss function, right? And so it's not that we have these different apartments that we're going to be picking from, or different models that we're going to be picking from. We're going to just try to find the ideal model, but basically we're taking into these account not just the mean squared error, which we want to shrink. We still want, that's still our goal, but we're also going to factor in the penalty of like how complex our model is. Okay, so now the question is, how do we measure how complex a model is, right? Obviously, if a model has a whole bunch of variables in it, it's more complicated. If a model has only one variable, we're going to say it's less complicated. Okay, but what goes into measuring how complicated a model is? And so you can read about this in regularized least squares Wikipedia page. In general, this idea of complexity is brought in this regularization term that we just call R on the function. So it's a function of the function f itself. Okay, so we're measuring the function f, and we throw it into R to measure like its complexity there. Okay, all right. So a simple idea is just how many coefficients are not zero. Okay, because we have model A. We can say model A. Oh, I have this labeled backwards, but model A fits a fifth order polynomial, and model B it's a fourth order polynomial. And basically, these are exactly the same, but all we've done is we've constrained the fifth weight to be 0, okay? And so if we say W5 is equal to 0, then we have a fourth order polynomial. And we can say, and we know the fourth order polynomial is less complicated than the fifth order polynomial. So we can just say, how many non-zero terms do we have in our weight vector? Okay, and that can be known as the L0 norm. How many non-zero terms? And that's very straightforward, but we run into a problem in that it becomes really, really, really difficult to optimize this. Okay, this loss function is not convex and it's disjoint. It's not a smooth loss function. So there's like it's kind of like it jumps from like 1 to 2. It's kind of like this discrete thing. So it actually becomes really difficult to optimize. You have to consider all of the different permutations of elements in W that are non-zero, and then when they are non-zero, what value should they actually be? And so this actually gets really difficult to compute. So we say, all right, well, what else can we do? Okay, well, instead, we can take the absolute values of our elements in the W vector. Okay, so now instead of counting which elements are non-zero, we're going to just take the sum of the absolute values. Okay, and we'll say this is going to serve as our measure of complexity, right? So values of W that are not 0, they get added in and contribute to our penalty factor. Okay, if a value of W is 0, then it's not counted in the complexity factor. Okay, now one thing that happens is that larger values of W contribute more to this measure of complexity, that complexity penalty here. Okay, so as you're doing this, basically your reduction in MSE has to counteract basically lambda times whatever size W you get. Okay, and this is known as lasso. Now, and then another one that we can use is the squared value penalty. So rather than taking just the absolute values of our W, we can square them and add them up. Okay, and so this is known as our L2 norm. Okay, it's kind of like Euclidean distance, the equivalent of that. It's the sum of the squared values. Larger values of W are heavily penalized. Small values of W are still penalized. They get added in here, but much less so. And this is known as ridge regression. Okay, and one effect of ridge regression is that it's going to end up favoring values that are of W that are kind of similar to each other and obviously smaller. We might have an objection, or you might have an objection, at least when I first encountered this, I had an objection, and it was, why do we count the size of the coefficient as a measure of how complex the model is, right? So I could get behind this, where how many terms are non-zero? If you have more terms that are non-zero, that's a more complicated model, okay? But if you have two models and they both have 5 terms, but one of these models just has bigger values than the other, why is that one more complicated? I had an objection to that, because I thought, well, both models have 5 terms. They should be equally complex. We shouldn't say this one's more complicated just because its coefficients are bigger, right? So I'll try to address these objections, right? So, okay. So what did I write? All right, so after all, if 2 models have the same number of variables, aren't they equally complex? Why is one model more complex or has a higher complexity penalty than the other if it has bigger coefficients? And if bigger coefficients mean more complexity, then can't we just change the units to kind of shrink the coefficients and reduce the complexity, right? Okay, so one, regarding the changing the units, we don't want to do that, okay? And so anytime you're going to use regularization, say lasso or ridge regression, it's recommended that you center and standardize your exit variables, okay? So centering means subtracting a constant so that the mean of each column is 0, and standardizing would be multiplying by some constant, some positive constant, so that the standard deviation of all the columns is 1, okay? If you are dealing with some kind of function that can't accept negative values, like you got the log function or something like that, then you can standardize in a way that scales everything from 0 to 1, okay? Or something like that, okay? So standardizing the variables, this addresses the concern that using different units will affect the size of the coefficients, right? Because if somebody measures something in pounds versus kilograms, then you're going to get different coefficients, okay? But standardizing them, you'll get the same thing. So always kind of standardize. So that's going to be the first thing, okay? But then even after you do that, so we can't play the units game anymore. How does the size of the coefficient measure complexity? All right. And so let's just kind of take an example and just kind of talk this through as far as, how does this reflect complexity? So let's say we have two models, okay? They have both the same input matrix X, centered and standardized. Both models have 4 variables, okay? And both models have the exact same coefficients for x1, x2, and x3. Okay, so these two models are almost exactly the same. But let's say model A has a coefficient of 1 for variable x4, and model B has a tiny coefficient for x4. Its weight for that is 0.01, okay? So with the exception of the value for W4, model A and model B are the same, but I would argue that model B is less complex than model A because it has a smaller coefficient. Okay? Basically, by having a tiny coefficient for that variable means changes in that predictor variable is going to have less of an impact on the output, right? So because model B has a tiny coefficient for x4, it's placing less importance to that variable x4. And so even though model A and model B use that variable x4, model B is really close to just ignoring x4, okay? So if you compare model A and model B is almost really close to ignoring that fourth variable x4. So we would say it's the simpler model, okay? Another analogy is you could imagine kind of two students, and they're both involved in like the same clubs on campus, okay? But one student is like an officer in all of these clubs, okay? So maybe both students are involved in like 4 clubs on campus, okay? One student is an officer in all 4 clubs, and so therefore, anytime there's a meeting, anytime there's some decision, that person has to attend all of these things and all of these meetings, okay? The other student also involved in all 4 clubs, but if they want to skip a meeting, they skip a meeting, okay? If something's going on and they don't feel like going, they don't go, all right? So maybe only marginally invested in each of these things, okay? I would say whose life is simpler, okay? The one who's only marginally invested, right? So even if they both have like the same number of events and things, the one who's less invested, okay, has the simpler life, all right? You don't have to kind of take into account everything there, right? And so I would say, by having a smaller coefficient, okay, on a variable, the model is actually simpler, okay? And so we can use the size of the coefficient as a measure for how kind of complex each model is. All right, so when we calculate the lasso penalties and stuff, we take our coefficients and we're going to look at either the absolute values of our coefficients or the squares of our coefficients for the ridge regression term. But one thing is you don't want to include the intercept, okay? So don't include the intercept because those aren't actually getting multiplied by any of our predictor variables. Yeah, question?
Is the parse of a linear regression function
I'm sorry?
In the parsnip linear regression function,
Parsnip?
parsnip package.
Yeah, in the parsnip package. Okay, yeah, what about that?
There's an argument called mixture, and if the mixture is 1, it's the lasso.
Yeah, okay, for GLMNet. Yeah, so I guess so. All right, so this is unrelated, but it's for 101C. You have Parsnip, yes, and Parsnip will allow you to create regularized linear regression models. And yes, we have a mixture term, which basically, do I have it on here? I think it might be in next week's lecture. But when you fit, say, GLMNet, you can say you have a term multiplied by the lasso component, the L1 norm. You have a term multiplied by the ridge component, the L2, and you have a mixture term that basically dials it from one side to the other. And so if you have, I think, mixture 1, it's entirely lasso. When mixture 0, it's going to be entirely ridge. And you can have like mixture 0.5, which is going to be a mix of the, like, I'm going to apply a lasso penalty and a ridge regression penalty type of thing. So it's just kind of like, how do you want to measure the complexity, right? And I'll show you what happens when you measure the complexity using lasso. I'll show you what happens when you measure the complexity using ridge, and then you can also kind of take a blend between the two. And so those are like when you're doing the actual practice of doing it on your computer, that's a term that you can kind of, I guess, a hyperparameter that you can kind of mess around with. But here we're getting into the, I guess, the nitty gritty of like what happens with these actual values themselves here. Okay, so if you're like manually calculating this, you would not include the intercept term. If you're using a computer package to kind of calculate lasso and ridge regression penalties and do regularized least squares, like, you don't have to worry about it because the computer package knows to do that. Okay, so to illustrate this, I have this very kind of simple two-dimensional data. Okay, x1 and x2 are on the same scale. I'm not going to bother scaling them. The true relationship, okay, the true relationship is that we take x1 and we multiply by 1.5. We take x2 and we multiply by 0.5. Okay, that's going to give us the true relationship. And here I'm going to just add some random noise. And I'm going to try to, based on my observed values, which include the random noise, I'm going to estimate my coefficients. Okay, and so currently, based on the random values that I've observed, my estimates are 1.458 and 0.45. Okay, the true values are 1.5 and 0.5. So this is just my estimated intercept and my estimated slopes for x1 and x2 using ordinary least squares regression. Okay, and I'm going to calculate. So I can calculate this using LM. I can also calculate my coefficients by throwing the loss function into an optimization function. Okay, so we haven't covered this directly in the class, but in R there's a function called optim, right? And basically it will calculate. You just give it some arbitrary initial starting value. It performs. There's different methods. One of them is related to gradient descent. BFGS is kind of related to gradient descent, and it's going to find the values that optimize, whatever function we have. Okay, so this function is just going to say, hey, calculate the ordinary least squares loss, and it says, oh, okay, the values that are going to optimize your ordinary least squares loss are 1.458 and 0.4533. Okay, so if I say, hey, I want to calculate the values that will optimize my loss function, it gets these values, which, as we would expect, matches the LM estimates. Okay. What I'm going to do now is I'm going to modify the loss function. Okay. Oh, here's the plot of the OLS loss function. And so with our data that we have, the optimal value is at 1.458 and what was it? 0.4533. That's this location here. And these are just kind of like the different contours for different values of the slope, slopes for x1 and x2. We get different things, okay? I want to just kind of show you what happens when we start modifying the loss function, okay? So here, this says calculate your L1 loss, okay, by calculating the ordinary least squares loss and add our penalty, okay? Our penalty is just going to be lambda times the absolute values of W1 and W2. So I'm going to take my vector of my W1 and W2 values and calculate the absolute values of them, sum them up. That's my L1 norm here. I'm going to multiply it by some value lambda. And we say, okay, just take that and add that to my ordinary least squares loss, okay? And then I'm going to throw this inside a wrapper and throw it into the function optim, okay? What ends up happening is that if, let's say I just got rid of this L term, all right? And I said, let's only look at this complexity parameter, right? So if we only cared about minimizing this L1 norm here, sorry, I've got the wrong L here, then the contours of the loss function ends up being kind of these concentric diamonds centered at the origin, okay? Because we, if you think about, so we have different values of W1 and W2. You know, I could end up picking, say, like 2, 0 or 0, 2, okay? And if I want to pick where W1, the absolute value of W1 plus the absolute value of W2 is equal to 2, right? I can end up over here. I can end up over here. I can end up at, like, say 1.1, 1.5, 0.5, sorry, 1, 1 or 0.5. You know, basically, I end up along this line. Okay. I could also end up down at -2, and this is what we have, right? 2, and that's what you have there. Okay. So this would be if you only cared about the L1 norm. Meanwhile, if we have W1, I guess I don't need to do anything. W1 squared and W2 squared, and we say that's going to equal 2. What do you get? You end up getting a circle, right? I guess with a radius, 1.41 or something. So this is what you get when you do ridge, and this is what you get when you do lasso. But so if you only care about L1, this is basically the contours, right? And you would end up picking, W1 and W2 to be 0. That will minimize this thing, okay? And so we have two things at play. One is the OLS function, which has these contours, these ellipses, okay, and that serves right here. And then you have these concentric diamonds over here, okay? And as you shift your lambda from 0, if lambda is 0, basically it's just the concentric diamonds, the contours. And as lambda gets bigger and bigger, I guess if lambda becomes infinity, then it just becomes these contours here, okay? And so what happens, this is the effect of penalizing, of increasing the penalty for complexity by increasing our different lambdas, okay? So our OLS estimates are 1.458 and 0.453. And if I have lambda some number, this gets a little bit bigger. These numbers shrink. If I increase lambda more, they shrink even more. If I have lambda equal to this, instead of 1.458, I have 1.23. And instead of 0.453, I get 0.225. Okay, so they shrink even more. So these are also known as shrinkage methods. Okay, so regularization is considered what we call a shrinkage method, because what it has the effect of kind of shrinking our coefficients. Okay, and as I increase my lambda more and more and more, basically they keep shrinking until one of them basically hits 0. And then here, I've increased my lambda to be so big that both of them have basically shrunk down to 0. Okay, the effect that it has on the, so if you plot the contour lines directly, this is what the contour lines look like. So here it is with a relatively small lambda. And I've drawn, these blue lines represent kind of, I guess the cross of where W1 and W2 are 0, okay? And what you're gonna see is, so on, just imagine kind of like trying to morph from all of these ellipses to something like with a bunch of diamonds, and it's gonna be kind of like, I'm gonna just kind of scroll through, almost like an animation. You'll see how it's trying to blend, or like go from one to the other, right? So as lambda increases to like 500 or whatever, now you get something that's more like diamonds centered around here, okay? So in the beginning, you start off with something that looks a lot like the ovals and the ellipses, okay? And what this red dot and the blue dot, the red dot represents the solution according to ordinary least squares regression, and the blue dot is our solution according to lasso, where we've had to kind of adjust it a little bit, okay? And so as I increase kind of my penalty, that solution kind of gets pulled down, diagonally down towards this thing, and our contours are, you know, like they have this weird shape. It looks kind of like an ellipse, but then also as soon as it hits one of the axes, they kind of take these tight turns of like, now the penalties get kind of applied to these things, okay? And so obviously, once W2 has shrunk down to 0, you're not going to get any benefit. Remember, the penalty is the sum of the absolute values of W1 and W2. And so once W2 is shrunk down to 0, you're not going to push it to be more negative or anything, because that's just going to increase your penalty. So you've basically gotten the like by shrinking W2 down to 0, like you can't shrink it any further. You can't reduce the amount of penalty. So all that's left is to decrease your penalty by shrinking W1, and so that's what ends up happening. So so at this point, W2 has shrunken down to 0, increasing the lambda is only going to have the effect of shrinking W1 until basically both coefficients are now 0, 0. Okay, and so that's summarized right there. Okay, over here we have ridge regression. The solution, basically, if you only cared about shrinking the W2 norm, it's a bunch of circles. Okay, and that's what ends up happening here, and so you end up kind of seeing the coefficients shrink and whatever, and in here you will see going from a bunch of ellipses to basically a bunch of things that look like circles. Okay, it has an interesting effect, okay, where if you look at the path the blue line takes as I'm kind of going back and forth, so with a small penalty and as I increase my penalty here, what we see is the blue line kind of traces out like an arc, right? It starts heading towards this diagonal line, and then once it gets close to the diagonal line, then it starts getting pulled closer and closer to 0, okay? That's what we see. All right, so what that means is that in the beginning, my W1 is 1.5 and my W2 is around 0.5. But as I increase the penalty here, what happens is that the W1 is forced to shrink and W2 ends up getting bigger, okay? And what it's doing is kind of pulling these values towards each other, where this diagonal line represents where W1 and W2 are equal to each other, okay? So it pulls these things towards each other, and then once they're kind of similar to each other in value, then they start shrinking together, right? And basically, what's happening is that as we shrink W1, okay, our OLS estimates get thrown off, okay, or basically our squared residuals get thrown off, and it turns out we can kind of improve the squared residuals a little bit by increasing the coefficient on W2, okay, to be something a little bit higher than what it actually is. And so that's what we have here, okay? So the larger coefficient is penalized more heavily than the smaller coefficient, okay? Shrinking that intercept, however, or not the intercept, shrinking the W1 causes the OLS function to grow, and so we reduce the OLS function by end up increasing the W2 coefficient, and even though increasing the W2 coefficient increases the penalty term, the amount the penalty term grows not as big as the reduction caused by shrinking the W1 coefficient, okay? And so that's what ends up happening, okay? If you look at these quantities for how we minimize ridge regression and lasso, okay, you can also think of this as in another form, right? So we have the OLS, the penalty, which is the residual sum of squares, and then we have a sum of lambda times either the sum of squares of our beta terms, which is ridge regression, sorry to switch from beta to W's to beta, or the sum of squares, not sum of squares, sum of absolute values of our coefficients, betas, okay? And this is in the form of trying to minimize a function subject to a constraint in the form of Lagrange multipliers. So if you remember, I don't know, whichever calculus class that was, Lagrange multipliers, you're going to say, hey, if there's a function we want to minimize, but we want to subject it to some constraints, you can include these kind of Lagrange terms here, right? And so we can also think of applying regularized loss by thinking of it as minimizing RSS subject to some Lagrange multiplier constraints here, okay? And so in that case, for lasso, your constraints are in the form of having the absolute values, okay? Which is going to basically be subject to these diamonds here. And then we're trying to minimize our RSS subject to the constraint that our terms have to kind of be along these circles of our betas, summing up to some value there, okay? And so the solutions are going to be where our kind of the ellipses of the OLS kind of intersect the edges of our constraints. And so for lasso, it's always going to kind of be at one of these corners here, which is going to be where one of the things ends up kind of shrinking down to 0. Okay. Why do we want to do regularization? Okay, so the reason why we do regularization is, again, it's another tool in our toolkit in terms of controlling our bias variance trade-off. Okay, so OLS, ordinary least squares regression, is unbiased. Okay, in the long run, the estimates from OLS will be unbiased. Okay, however, there is a lot of variation. Okay, it is if two people take the same take different data sets from the same population, we're going to get different estimates. And so we say there's variation in our estimates, and OLS gives us the best, what is it? The BLUE, right? The best linear unbiased estimators, right? So they are unbiased, and as far as all of the unbiased estimators that exist out there, OLS has is the best in that they have the least amount of variation, but there's still kind of variation there. And so you can reduce the variation by now including bias, right? So in terms of our bias variance trade-off, we can, if we want to further reduce the variance, we can, but now we have to introduce bias. And that's what regularization is going to do. So here, this is just like, I'm going to plot out a whole bunch of these things here, okay? And so this is, this ellipse, or this cloud of points is what would happen if I take my data set, okay, or if I take the true model here. All right, so the true relationship is that we have a slope of 1.5 for x1 and a slope of 0.5 for x2. That's the true relationship, okay? But when you do random data, okay, so the true values are 1.5, 0.5, okay? But when I take random data sets, sometimes I get a higher coefficient for W1 and a lower coefficient for W2. Sometimes I get something else. And so these represent 1,000 different random data sets. There's 1,000 little dots here, okay? And these represent all of the different data sets that we could possibly get, okay? When we just take random samples centered around that true model there, okay? When I apply lasso, okay, these are all of the values that I estimate, okay? And it looks like you just have blurred vision here, but what's happening here is that basically the entire cloud of points just gets shifted down diagonally by a little bit. So this dot gets shifted down a little bit. This dot gets shifted down. This dot gets shifted down, okay? So with OLS, this is unbiased because if you take the average of all of these points, okay, the average of all of these is going to be at the true relationship, 1.5, 0.5. Okay, that's the unbiased part. Okay, when you take the average of all of these things, the red dots, it's no longer centered at 1.5 to 0.5. It's, you know, shifted down a little bit, maybe 1.4 and 0.4 or something like that. And you go, well, that's not great. Why would I ever want that? Okay. What happens? Okay, so everything gets shifted down diagonally. Okay, like everything gets shifted down diagonally, except the ones when they crash into, like, where this point should have been shifted down. What happened? It didn't get shifted down. It like crashed into the this axis where it's 0, and so just kind of this one got zeroed out. Okay, and so as I increase the lambda penalty, that you can see all of these dots get kind of pulled down a little bit. Here we've increased the lambda penalty quite a bit more. And so the entire cloud shifts even further. You can see, again, this dot shifts down to here, this dot shifts down to here, and so on and so forth. But now a bunch of these points have like crashed into where W2 is equal to 0, okay? And so, you know, these ones didn't get shifted down, they just got zeroed out, okay? And so in this regard, the amount of variance has shrunk, because now some of these things have zeroed out, okay? And if I continue applying an even greater penalty, like the entire cloud shifts down even further, all right? And so, you know, the center of these things is terrible, right? Like this has high bias, okay? But we have zeroed out some of our coefficients. So lasso can be useful and effective in, like, it shrinks down the coefficients, and you can kind of, some of the coefficients will get shrunk down to 0. So in a kind of a loose form, lasso can be used as like variable selection, okay? So it can kind of zero out some of our our variables in that way. But you can see the center of this cloud of points is around the true value of 1.5.5. This one, the center is like way off, okay? So now we've increased your bias, but as far as like how much spread is there in the cloud of our dots here, it's a lot smaller, less variance here, okay? OLS does something similar, okay? So here's the plot of all of these things, and you can see they've all kind of crashed down. The final one that you can barely see, if I increase my penalty a lot, then everything just zeroes out entirely. There's just a stack of blue points right here at 0, 0, okay? And so here is, you can see how the cloud of points just get shifted until it crashes into the x-axis where they all just kind of zero out here, okay? Similarly, for ridge regression, you'll really see how the variance, how the size of this cloud shrinks a lot, okay? So with ridge regression, we are really reducing the variance, okay? Oh, I've forgotten again. I've given you 2 answers. I'll go ahead and give you your last 2. Third answer is A as in apple, and the fourth answer is D as in dog. Okay, A as in apple, D as in dog. Okay, so for this one, we're going to apply increasing penalties of ridge regression, and for ridge regression, this cloud of points gets shifted, or will just kind of shrink, okay, into like a tighter and tighter ball, okay? And so here is like this cloud of points for different values of penalty, and you can see the cloud of points get shrunk over here, and shrunk over here, and shrunk over here. But it's the same kind of like applied to the same thing. So if you like pay attention to like there's like this weird thing with like these 2 dots and 2 dots here, like these 4 dots right here, you can see that kind of structure also exists right there, and then also exists right there. And so these, it's, we're looking at the same data sets, okay, but we're applying the regularization, the shrinkage, okay? So when we shrink these 4 dots, okay, they form the same kind of pattern here, and they form the same kind of pattern there, right? So it's kind of this interesting shape that ends up getting plotted there. But that's what we have, and so you can see what is the spread in our different kind of coefficient estimates. We get less and less variance, okay? So again, the idea of like variance here is, are my estimates the good estimates, right? Is my estimate for W1 and estimate of W2, are these good estimates? And there's a couple things. One is the bias, right? If the true values are 1.5 and 0.5, are my value estimates of W1 and W2 going to be centered around 1.5 and 0.5? So OLS, they are unbiased, okay? But when you have a random data set, you don't know if you have this one where like your W1 is really big and your W2 is like way too small, or if it's this one where your W1 is too small and your W2 is too big, okay? So you have a lot of variance, okay? By applying some kind of regularization, you can shrink that amount of variance, okay? And so like if you look at the red cloud of points, it's a lot smaller, and so we're not going to be, it might be too big or too small, but how much one set of coefficients varies from another is going to be a lot less. However, the center of all of these things is off, right? There's bias now, okay? So we're introducing bias. That's the cost of applying regularization, is we're introducing bias, but now we have less variance in our estimates there. Okay, that is it for today's lecture. So this is just kind of an idea. Yeah, we have a question.
So then is the main advantage of using lasso or ridge if you are trying to lower the total number of coefficients you have?
So lasso and ridge, we employ them as, again, in our toolkit of, when we're trying to fit models, we're often trying to swing from one side of another to on this kind of bias variance trade-off. And so if you're in a situation where you want to reduce the variation, okay, or variance, and you're okay with introducing bias, this is an option that's available to you. So yeah, for lasso, it can be kind of it can be used for variable selection in terms of like, can I throw away some of my variables? And you can use kind of lasso as kind of a rudimentary first pass, and it's going to just throw some variables away, and then you can kind of refit later after kind of doing this form of variable selection. With Ridge, it's, I don't know. It ends up kind of pushing coefficients to be kind of similar to each other in size, and you can see this, like this is, you would never do this in real life where you've increased the penalty so much that like everything's like the same and it's like way biased. But maybe something around here is okay, I don't know.
And so like with his example around the package where you can kind of adjust how much.
Yeah, so yeah, these are, again, these are all kind of tools available to us to kind of fine tune and tweak our models. These illustrations here are kind of like taken to the extreme, so it kind of brings attention to like what is the effect of this thing, right? It's kind of like you learn the effect of like what the knob on on your stereo system does by like cranking it all the way to the end, and you go, oh, that's what it's doing to the music, right? Like when you have these different knobs and you're like, okay, let's turn this all the way up. Oh, okay, I can actually hear the difference. And so, but in real life, you would never actually crank it all the way to the max and things like that. And so, so again, these are just like, this is what this knob does, and that's what we have. That said, regularization has fallen like as a tool by itself, not linear, like GLMNet, you can fit a linear model with regularization all by itself. Probably not very popular because the performance of it isn't going to be great. However, it is, regularization is used as kind of like a fine-tuned adjustment in, say, like a broader model. Like if you want to fit neural networks or something, you might have one layer in there where you apply some regularization to the coefficients and the estimates of that particular layer. So yeah, used all by itself, probably not so much, but used as something to kind of refine things, I'd say it's probably more popular in that sense. And again, these lectures and these slides are kind of just an illustration of like what happens if when you crank it all the way up, so you can really kind of see what the effect is there. Okay, we'll wrap things up here. We'll see you guys on Thursday.